All right, today we're going to start a new unit, and the unit is dealing with bonding, and we'll get into some nuclear chemistry after that. So we have a learning target today. What did you write down? Breck, what do you think? Okay. How electronegativity is related to a bond. That's definitely something we'll be talking about. That's probably more on my classification that I'll put into a success criteria. Okay. What'd you put?
Understand ionic and covalent bonding.
Okay. Understand the different types of bonding, ionic and covalent. Good. So let's look here. Let's look at what the actual learning target is. It is to identify the types of chemical bond that identify the type of chemical bonding that has occurred in a given compound. So, in order to do that, we're going to need to predict the possible interactions between atoms based on their valence electrons. What do we say valence electrons were? Yeah. Electrons on the outermost energy level. Excellent. Okay, so we're going to need to be able to do that. What else? What else? Well, explain the tendency of elements to either transfer or share their electrons. That's the whole idea with the different types of bonds. Either we're transferring electrons or we're sharing electrons. Transfer is ionic, sharing is covalent. Our third success criteria is what Brett was hitting on there. Predict the type of bond between the two atoms, whether it's ionic, polar covalent, non-polar covalent, using the difference in the electronegativity. So we're going to need electronegativity, so why don't you take out your periodic table? We're going to need to use those. So we might as well grab those and take those out. Okay, so types of chemical bonding. We have two types of chemical bonding we're going to be dealing with: ionic bonding and covalent bonding. As I alluded to earlier, that we are sharing, we are transferring. So in this diagram right here, I see two different types. Right here on the left-hand side, it says the transfer of electrons. So just very simple, this electron right here transfers over to this atom, okay? So we have a electrostatic force, a positive and a negative, that hold these together. This is covalent bonding on the right-hand side, and what happens is these two atoms share both of the electrons, okay? So there is the sharing of electrons. So the difference between ionic and covalent, one is being shared, one is being transferred. Now, I got a bunch of this writing here. I forgot to take that off of my slide, so I'm going to have to get that off of the slide here. But here we go. Ionic bonding is chemical bonding that results from the electrical attraction between cations and anions. Remember talking about ions, cations, anions. Remember? Little anion, she's negative. Okay? So anions are negative ions. Cations, I always remember, looks like this little guy right here. That T looks like a plus to me. So cations are positive ions. Little anion, she's a negative one. If I look right here, what is actually happening? Okay? We talked about electron configurations, and we talked a little bit about how they want to fill their outermost energy levels to become more stable. All right? If you look at lithium right here, on this electron right here, that would be the 2s1. So I have 1s2, 2s1. So I only have one valence electron. If you look at fluorine here, okay, I have 1s2, 2s2, 2p5. So on my valence level, I have 7 electrons. Fluorine only needs 1 more electron. So when lithium gives up this electron to fluorine, its shell right here is filled. Because remember, the first energy level only has a s sublevel, and it fills with 2 electrons. And by giving fluorine that electron, this energy level is filled with 8. Now, lithium has 3 protons. When it loses that electron, it only has 2 electrons. 3 pluses and 2 minus gives me a net charge of +1. Here, fluorine. Fluorine has 9 protons. It gained 1 electron, so it has 10 electrons. 10 minuses, 9 pluses gives me a net charge of -1. So, main group metals, just a generalization, main group metals lose electrons to form positive ions, which are cations. Main group nonmetals gain electrons to form negative ions, which are called anions. Covalent bonding is the sharing of electrons between the 2 particular atoms. So, if we look right here, here are 2 hydrogen atoms. Each hydrogen has a 1s electron. If they share these 2 electrons, if you look at this hydrogen, it has 2 electrons. You look at this one, it has 2 electrons. They are sharing 2 electrons in a covalent bond. So transfer, ionic bonding, sharing, covalent bonding. Now, how do we determine whether it is ionic or covalent? Whether the bonding is ionic or covalent? Okay. We never have purely ionic bonding, and very rarely do we have purely covalent bonding. We do have purely covalent bonding, okay? It's usually when something bonds to itself, okay? Usually when it bonds to itself. So, rarely do we have purely covalent, and we never have purely ionic. It's a combination, so to speak, of the 2 different types of bonding, okay? The degree to which bonding between atoms of 2 elements is ionic or covalent can be estimated by using electronegativities. Now, who can tell me what electronegativity is? We just talked about it in periodic trends. What is the electronegativity? You've already answered one. Okay? Sarah says it's a measure of the atom's ability to attract electrons. Exactly what I have right here. Good job. So, attracting electrons. Who wants to attract electrons? How about the halogens? Okay. What has the highest electronegativity on your periodic table? Fluorine. Okay. Fluorine. So, we're going to use those electronegativities to determine what type of bond it is. So, we set up what I call ranges or bins. Okay. Ranges or bins. So our nonpolar covalent bin, okay? A nonpolar covalent bond is a bond in which the electrons are shared equally by the bonding atoms, okay? They are shared equally. They have an ionic character of 0 to 2% and a difference in electronegativity of 0.3 or lower. Now, find this on your periodic table. It's usually what I call the back of the periodic table. All right? It says it's the percent ionic character. On the top, you see the difference in electronegativity, and on the bottom, you see the percent ionic character. So, we just said that a nonpolar covalent bond, okay, is 0.3 or below, which corresponds to 2% ionic character or below. Well, if something's 2% ionic, That tells me it's about 98% covalent, right? So that's a lot of covalentness. So that is what we are meaning by those ranges. Now, let's look at iodine, okay? Anna, why don't you go ahead and find me the electronegativity of iodine? Find it? 2.66. Excellent. Everybody with me? Iodine's 2.66. So in this particular case, okay, I have a 2.66 for one iodine. The other iodine is a 2.66 also. My good math tells me that that equals 0. So by subtracting those two to get 0, I have a non-polar covalent bond, because that is definitely less than 0.3, correct? Now my second range is for the polar covalent bond. In a polar covalent bond, the bonds are shared, or excuse me, the electrons are shared unequally. The electrons are shared unequally. Think of it as a tug of war between the two different atoms. One atom is tugging a little bit harder, winning that tug of war. All right? So, greater than 2% ionic character, less than 51%. And on our chart, that corresponds to greater than 0.3 and less than 1.6. So if I find that range in my electronegativity difference, that gives me a polar covalent bond. Okay? So, Isaiah, I'm looking here at hydrogen and I'm looking at chlorine. What is chlorine's electronegativity? 3.16. Okay? Madison, what is hydrogen's? 2.18. So if I take 3.16 and I subtract 2.18, that gives me a 0.98 difference. Does that fall greater than 0.3 but less than 1.6? Absolutely. So we'll throw that into the polar covalent bin. Now our third bin is with ionic bonds. Ionic bonding, remember, is the transfer of bonds. So there is a really uneven distribution of charge. Greater than 51% ionic character and ranging from electronegativity difference of 2.1 to 3.3. Really, you can just think of it as above 2.1 is going to be an ionic bond. All right? So, as I'm looking at this, Gabe, what is chlorine again?
Chlorine is 3.16.
3.16. Okay, Landon, what is sodium? 0.93. So when I come up with my math on that, I get a 2.23. Is 2.23 greater than 2.1? Yes, it is. So we'll throw that baby into the ionic bond. Okay? Now, what's the problem? All right, Lauren says there's a gap between 1.6 and 2.1. Absolutely. Okay? Absolutely. So, we have a fourth rule, okay? A fourth rule to deal with, and that is when we fall in between 1.6 and 2.1, okay? When we get into that area, we need to check. Do I have a metal or do I have a non-metal? If I have a metal, it is ionic. If I have a metal, it is ionic. If I have a non-metal, it is polar covalent. Okay? So if I have a metal and a nonmetal ionic, two nonmetals, polar covalent. Now, you're going to ask, what about a metalloid? I'm going to show you that here in a little bit and how I do that, okay? Because this does not say, it says a metal or a nonmetal. It doesn't say anything about a metalloid. I'll show you how I do the metalloids here in a minute. So let's look here. Magnesium is bonded with chlorine, okay? Magnesium is bonded with chlorine. What is my electronegativity for chlorine again? We did that. It's 3.16, was it? Okay, 3.16. What about magnesium, McKenna? 1.31. So when I subtract those, I get a 1.85. That falls in my range, doesn't it? Okay, that falls in the range. So I need to check, do I have a metal? Paige? Yeah, what's my metal? Magnesium is a metal. So do I have a metal involved? Absolutely, Paige says. So that tells me that since I have a metal involved, I throw this into the ionic bonding bin. Now, we're going to just go through some and work some and say, all right, are these ionic or covalent bonds? And if it's covalent, what type? Okay? So, okay. I'm glad I remembered to put this in. This reminds me, folks, you're going to see these numbers. See how this number varies a little bit different? Okay, I told you 1.6, and this says 1.7. Well, it's really going to depend on what kind of book you're using, a textbook, and it can change from book to book. The reason I gave you the 1.6 is that's what WebAssign uses. Okay, so I took my ranges right off of WebAssign. Now let's go through and do some independent practice. So get yourself some scrap paper, okay, some place where you can just write down some stuff and do some of these. Because you're going to tell me what type of bond we have. So as I look and I click, what type of bond between carbon and hydrogen? All right, I look at carbon, I look at hydrogen. I can see that when I turn it to the correct side of my periodic table, carbon has an electronegativity of 2.55. Hydrogen is 2.18. Okay, will we agree on that? All right, so when I do my math, let's see, my 5 I've got to borrow, so I get a 7. 4 and 1 is 3. I get a 0.37. Now, 0.37, it's got to be 0.3 or below to be a nonpolar covalent. So I'm saying since my value was 0.37, that I have a polar covalent bond. Now, let's just make a guesstimation, okay, how much ionic character that is. So I'm looking at my chart, and that says 0.37, okay? So that's falling somewhere in between the 2% and the 4% ionic character, because 0.3 is 2%, 0.4 is 4%. So I'd say that this is a little bit under 4% ionic character. What type of bond, ladies and gentlemen, between zinc and oxygen? What type of bond? Oxygen. 3.44 electronegativity. Zinc is a 1.65 electronegativity. I need to borrow once again. I have a 9. I need to borrow again. I have a 7. 1.79. Sound right? Now, I look at this 1.79 and I say, okay, that's not over 2.1, so I'm in that range of the 1.6 to the 2.1, correct? So I ask, do I have a metal? Yeah, zinc's a metal. So what type of bonding? Ionic. Okay? Ionic bonding. What type of bond? Between silicone and fluorine. What type of bond? What type of bond? Well, I know fluorine's got my most electronegativity. Okay? Fluorine is a 3.98. I find silicone there. Silicone's a 1.9. So I get 2.08. So once again, I'm falling into that range of unknown. Okay? So I ask myself, do I have a metal? Do I have a non-metal? And up, here we go. I've got a metalloid, don't I? Okay? Now, what I tend to do with these metalloids, okay, is I look at what 2.8 is. I see 2.8 on 2.08. Okay? So 2.0 is 63% ionic, 2.1 is 67. So I'm somewhere in the 60s of ionic, right? So then I say, okay, I'm going to classify that one as an ionic bond. Okay? I'm going to classify this one as an ionic bond because it is closer to that 2.1 than it is to the 1.6. Now, my final one. What type of bond? Germanium and hydrogen. Germanium, 2.01. Hydrogen, 2.18. My difference in electronegativity is 0.17. So what type of bond is going to be formed here? Non-polar. A non-polar covalent bond. Okay? So basically, all we're doing is looking at electronegativities and comparing. Remember, what is electronegativity? The ability to attract electrons. So if somebody has a higher electronegativity, they're pulling those electrons more than the one with the lower electronegativity. So it's just all a big tug of war of electrons. All right? So far, do you think you could tell me what type of a bond it is, given the two things? Let me see thumbs up. All right. Awesome.